Alright, and greetings programs, and welcome to another LeetCode adventure. Here we're going to be tackling a new problem, so let's go ahead and jump to it here. We've got number 4, median of two sorted arrays. This is a hard problem, so this will probably take a little while, and we'll probably have some issues here and there. But let's give it a shot, right? So, given two sorted arrays, nums1 and nums2 of size m and n respectively, return the median of the two sorted arrays. The overall runtime complexity should be order of log n m plus n. Okay, so example 1. Input, we got an array of numbers 1 and 3, and they're sorted, which is good. And we've got an array of numbers 2, and they want us to output 2 as our answer. So they merge the array, so you get 1, 2, 3, and the median is 2. Okay. And then here they've got 1 and 2, and 3 and 4. And their output is 2.5 because they merged the array. And then they get a median of 2 and 3, so they're like right in the middle here. And it says add the 2 together, and then divide by 2, gives you the 2.5. Okay. Okay, so numbers.length is m, numbers2.length is n. M is between 1,000, 0 and 1,000, n is between 0 and 1,000, but m plus n is between 1 and 2,000. So at least one of them has to have a number. You can't have two empty arrays, so that's good. And the numbers can be from negative 10 to the 6th to 10 to the 6th. Okay, so they're going to tell us, let's go check what function they give us. So they're giving us a vec of i32. So they tell us basically we're going to be containing i32. So I don't have to worry about this, really. Excuse me. So let's see what we then have. They want order of log m plus n. So if we go to merge the arrays, I mean, we have to go through each one, so that's order of m and n. So to do a log one, the only way that I know to go to log is to do the half sorting of a binary search. So we'll do that. So obviously we're going to do a binary search to meet their requirement. Okay, I like these to be on the new lines. There we go. Now, I've increased the text here on the code side and on the problem side so that everybody can see it. So I'm at like 150% zoom in. So I'm going to make this take up the whole screen here. All right, so we're just searching for the median. Okay, so let's just say we're going to return 0 for our default. Okay, so we have two arrays. It'd be easiest, I think, if we only had to search the smallest of the two arrays, because then we're searching less. So let's find the big and the small. Let small be a vec pointer of i32s. And that's going to be nums1, right? No. It could be either one. So if nums1 is less than nums1.len is less than nums2.len, then the small one will be nums1. And we just want to pointer that. Now we're taking a reference here so that we can not duplicate memory. We're just trying to stay in the same memory space. We don't want to, create two brand new arrays and then have our memory be m plus n, we want to have our memory be order of 1. And then if it's not that, then it's obviously got to be the other one. And nums 2. And we'll assign those. Okay, so that looks good. Do the same thing for big. But this one has to be the greater than. Okay, nums 1, nums 2. Okay, so that looks good. And then what do we have to do after that? Let's see if we have binary search. We need a left and a right pointer. So let left, and these are going to change because they got to move through the array. So let left be 0. We want to search through small, so let the right be small.len. All right, so that sets up our array. So we have 1, 2, 3, 4, 5, and basically we're looking at left, 2, 3, 4, and then right. Well, yeah, so if I go ahead and print those out, you should see that print line left and right. So left, right, left and right. So if I print that, oh, it doesn't like something there. Okay, well, let's check and see what it doesn't like first. Oh, because I just said nums. Nums 2. There we go. Okay. Print line is a macro. Right, so what do we print out here? We printed out 0 and 1 on that one. But our min is just 2. So let's go to this test case. So 0 and 2 is what we printed out. 0, 1. So right there, our max, our right one is a little bit high. So we want to probably do that small n minus 1. Okay. Because we want to be able to say, hey, look at the right and not be out of bounds. And if our bounds here is saying that it's 2, but we only have 0 and 1, we'll be out of bounds. We don't want that. So small n minus 1. Okay. Because we're 0 indexed. Very good. Run that. Okay, 0 and 0. Cool. Case 2 will be 0 and 1. Awesome. And then if I add a case in here of, let's bring this up. We'll just say 1, 2, 3, 4, 5, 6, 7. And then we're going to duplicate that down here. Okay, run that. And then that should show me 0 and 6. 0 and 6. Perfect. Okay. So we're looking good there. Let's go ahead and print out to make sure we got the small ones right. This is just to help me as we're going along. So we'll do a print line, small, and then I don't think vector has display defined, so we're going to just use the debug because I know that the debug one is there. So we'll go ahead and we'll print out what we got for our small. We'll print out what we got for our big array. That way we can make sure we got them coming through properly. And being defined right when we're doing when we're reading through and doing our tests. Left and right are very important. We're actually just going to call these out. Okay, that looks good to me. We don't need this. We can do that with, there we go. Okay. I like that. That's a good print statement. All right, so we have our left and our right for our searching. We have our arrays. Now we need to search. So when you're doing a binary search, you're basically searching until your left and your right have met. So while left is less than or equal to our right, we're going to do something. Now, let's see, what are we going to do? Well, we need to find the midpoint that we're looking at, because we're going to be going and moving in a binary search tree. So we would do a, like, if your midpoint is less than your right, so if your right is greater than your midpoint, then no. We'll do it as the left. If the midpoint is less than the left, they move the left to the mid. So that would be the left equals mid plus 1. Otherwise, you can move your right, right? Yeah, right equals your mid minus 1. And then there's your binary searching right there. But we haven't defined this mid yet, right? Now this works here because, let's go ahead and talk through that. So if I have an array of, let's say, 1, 2, 3, 4, 5, 6, 7. And then let's say that we look at 4 for our mid, and our 1 is here, and our 7 is here. If the value that we're currently looking at, so number 4, right? So I guess this would be more of a, we'll just say small mid for now. If our small's middle value, right, is less than our target value, and target val, right? So let's say our target val that we're looking for is a 5, right? And then our mid that we're looking at here is 4. Then we want to move our left, which is currently 1, up to our 4 plus 1. So we'll just say our target value was 6. 4 plus 1, so we're here looking at 5 during our next iteration. So 5 and 7, and our mid would be 6. And then we'll know that we found it, right? But that's just doing the binary search. You're cutting your array in half each time and checking. Okay, so we need to do that, we know. But we need to find... We have two arrays that we're searching through at the same time. And we need to calculate that middle point on the arrays, on both arrays. So let's calculate our current middle point on the small array. That's small middle point. And that's a U size because we're looking at the index in an array. So that's going to be your right plus your left over 2. No, what is our array size? Okay, so we're only going to get up to 2,000 elements, 1,000 per each array. So right plus left won't overflow. Right and left are U size as well, right? Oh, I didn't decide. It's supposed to be U size. And that should be a U size. Because, again, we're looking at the index into an array. Okay. So the right and the left... if we don't want them to overflow, we can do a little bit of a simple thing here. If you have right plus left divided by 2, we can move this left out of here, which should give you a right divided by 2 plus a left divided by 2, which should give you... Let's go ahead and expand this so we can just look at code. Which should give you a right divided by 2, right divided by 2, and then it's a minus left divided by 2 plus 2 times left over 2. And then that gives you the ability to just say that this here is the number left. So then you get, and I know it's a little convoluted, but it's just to move the right minus left. If I did that right. Right minus left over 2 plus left. And we'll put some parentheses there, make that clear. Okay, so what you're getting out of here is if we take the right minus the left, then we won't overflow because this has to be within bounds. We subtract, so we're going to be within bounds. And then you add the left on in, and you're guaranteed to be within bounds. Now, the nice thing is that mathematically keeps you in on your high numbers, but we don't have to worry about that here because as far as this is concerned, there's not going to be an overflow because it's only 1,000 max per array, so 2,000 total. So let's just... So there's no overflow, not needed for this small of 1000. Okay. But we can do it that way. So let's. It doesn't really hurt us much. It's a small operation change. Okay, so that gets us a midpoint in our small array. Now we're comparing two arrays, though. When you're comparing two arrays, and we don't have a target value that we're looking for, so we need to figure out our target value. So we're looking at the middle point, and we have to calculate a median. And we're going to be checking our median on the left, or on the small array, and on the big array. So let's get our thing that'll let us calculate our median point, right? Of the small array. So let small min, and this is just the left-hand side of the, this is the value. This isn't the index. So this is the values on the left-hand side. So that would be, what? Small array, small middle minus 1. And that'll put us on the left. And then we're going to do the small max. That's an I-33. Oh, there's got to be equal signs. That's an I-32 as well. But that one, we're just going to set it equal to the small mid because we don't want to space 3 out. We just want it to be spaced 2 out. Okay. That looks okay. So let's go ahead and print those out so we can see those each iteration. So do small, and then there's our midpoint, and then we'll do min and max. Small mid, small min, small max. Now we don't really have a target value because we're looking for the median. So we're going to go ahead and blank this out for now. And it's probably just going to loop forever. So we'll go ahead and we'll say return 0.0. I just want to see what I get for one iteration. Okay, so we're getting a runtime error. It doesn't like this. Let's go see why it doesn't like it. Index out of bounds. Small mid is out of bounds. Small min minus 1 is out of bounds. We're overflowing. Okay. Why are we overflowing? So small mid is saying that it's 0. 0. What do we... Small is 2. We're looking at 0 index. Okay. I see what's going on. So... Okay, if that's the case, then we can't have you go under. So if small mid is 0, then I guess just return. You're gonna be a minimum value, so we're gonna return the I-32 minimum instead. Otherwise, we'll just return the array value. There we go. Okay. Now, if I have that problem with the min, and that's because the index is going too low, so then if the index goes too high, I'll have the problem with the max. So if a small mid is small dot length, then small dot length minus 1. Now I want to return like I-32 max, because we turned the min up here. I want to just have a ginormous number up down here to test with, right? So what does that get me? Wrong answers, at least. Okay. Well, wrong answer is what I expect at this point, because we haven't really done the algorithm. So small is 2. Small mid then is found to be the 0 index. And we're getting small being ginormously tiny or super tiny. And we're getting the max to be super big. One of these should be the number. I mean, one of these has to be the number. So why? Okay, we're saying 0 index. But up here we're checking to see if our 0 index is... Okay, alright. I see. Because we already took care of it being in the 0 or less than it. So if we're over, we don't need the +1 or the -1. Okay. Okay, that makes sense. Alright, so what do we got then? Yeah, so 2. Okay, so we got max of 2 and we got a min of just a bunch of stuff. Okay, then how's that look on this one here? So 3 and 4. And something's going on here. We're not getting our small array, because that should be 1 and 2. Let's go look up here. So why aren't we getting a small array? They're equaling the same. If len1, because they have the same length. Okay, so one of these guys has to win out. So if len1 is 2 and nums2 is 2, then len1 goes there. And if len1 is greater than nums2 dot length, then return nums1. Otherwise, you're not return nums2. Okay, that should solve it. Let's go back and look. This one here, small is 2, big is 1, 2. Okay, yeah, there we go. What about case 3. They're the same. Okay, cool. Yeah, that works. That works. I guess actually I should test. What if they're 1, 2, 3, and 4, 5, 6? Then I should probably just do a quick test case of if there's nothing and there's only one element. And then a test case where there's nothing and then there's like 3 elements. But we can swap the nothings so that I know that it's getting the right minimum arrays. Okay, let's do that just to see. Right, so now our index is out of bounds. Ha 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 ha. Length is 0, but the index is. See, we're finding issues by throwing in extra test cases. Okay. We're still in here. With an issue. Oh, I wish I had a debugger. Okay, so let's... Is there a way to, like, shrink you away? There we go. Okay, now we're half. Half and half. So here our length is 0, and we subtract the 1, and we're getting out of bounded. What happens if I just remove this -1? We'll just see what we end up with. Are we in the proper bounds then? We are. And the world does not blow up. This doesn't seem correct. Small mid is 1. So then we've got 1 and 2. Oh, no, that's right. Okay. Okay. I can deal with that. Okay. So I was wrong on the assignment there. Right. Set it to the right of the array, I guess, instead of right -1. My apologies, compiler, but thank you for showing me that I'm wrong. Okay, so let's go ahead and what do we have now? We have our small median, or our small midpoint. We do the min and the max. But we're looking for the median value. So to do that, we need to get a big midpoint, right? So let big midpoint equal U size And how are we going to search through this? Like, how do we figure out where to be looking? Because our points move in the small array, But how do we search through the big array? Let's think about that for a minute. Let's go ahead and grab these two. And we'll convert those to big values. So 27, 28. There we go. Okay. So how do we figure out this big mid? I guess if we took the arrays, we could put them together. And then that's the one that's moving. Because that's the only one that's calculated off of right and left. And right wouldn't be valid for the big array. So yeah, let's put the two of them together. Let's just say that it's this equation up here. But now, instead of our array being right to left, we're going to have the two giant arrays sizes. So that'd be like small dot len plus big dot len divided by 2. Right? And then we're going to want to move in there. So subtract the midpoint on the small one. So if this, let's say this is 0 and this is 0. You get 0 divided by 2. No. Or at least want 1. So we'll add a 1, I guess. I'm not so sure about this part. I think this should work, if I remember things correctly. Okay, so then we can go ahead and do a print as well for this. 31 s/small /big /g. Okay. Oh, it should not have met that one because that was a capital S, but whatever. Okay. I guess that works. Now we can work on our movement. So we're going to get rid of this. We don't need that. Okay, so now if our now we have 2 arrays, right? So let's cut these down here. So now we've got 1, let's say 5, 6, and 7. Okay, so we're looking through the smaller one of these. So we'll go like that. So looking through the smaller one. And low, high, and mid. And we need to know when to move. We kind of just know a mid in here based off of these ones. So our mid was 1, 2, 3, 4, 5, 6, 7, 8. Divided by 2 was 4. Minus 0, 1. So 4 minus 1 is 3, so 0, 1, 2, 3. So I guess we're looking at number 4 first. Okay. But we need to be able to tell. So 4 would be our big one's max. 3 would be our big one's min. Here it would be big small max of 6, small min of 5. So if our big one's max, if our big max is less than our small's min, right? So if our big one's max, so if like 4 is less than our small one's minimal, which would be like 5, then we want to move the right to the mid minus 1. So you want to move the right one here down to here. And then otherwise, we just move the left to the mid plus 1. But these need to be the small mids. I think that works. That seems right. So we're searching through the small array. Small mid 0, big mid 2. Small mid 1, big mid 1. Let's go and check it on something like, yeah, this guy here. Okay. Small mid starts out at 3. Big mid starts out at 4. I think they'd be this. Okay. Small mid goes to 5. Big mid goes to 2. Small mid goes to 4. Big mid goes, but it stops. And it looks like we're bouncing halves. 3 and 4. 5 and 2. 4 and 3. Okay. So when we find it, what are we going to do here? Okay, so if we find it, how do we know if we find it? Well, then the big max. So in this case, we'll say right now 4 would have to be bigger than the smaller min. So 4 is greater than or equal to the smaller min, right? I think. So if the big's max is greater than or equal to the smaller min and the big's minimum value is less than or equal to the small max value. Yep, that should tell me that I'm right there. So then if that's the case, then we're going to return. Do we return the small min or the big min? Return small min as a F64. Well, we finally got one. What do we get here? When it's odd, we've got it. When it's even, we don't. Okay. We got 2 there. That's fine. When it's even, we got 2, and it should be 2.5. So it matters on if it's odd or even. So small dot lang plus big dot lang modulus 2 is 0. There we go. There, just to be concise. So then when it's odd, we gotta do like return small min plus the small max. Small max. As an F64, then divide that by 2.0. Is that getting me there? No, that didn't get me there. Do. Okay. Small min and small max. 2 and some ginormous number. When I want it to be 2 and 3. Right? Yeah, because I want to... I'll take the max and the mins and the mins and the max. Let's do it. Compare max of the mins. Big min. And standard compare mins of the max. Big max. And I guess that means I should probably just do that here. Standard compare the max of the mins. Big min. Oh, there we go. All right, we did our binary search. Nice. Nice. It handles these edge case guys nicely. Okay. I mean, that looks pretty good. And it handled that giant one, right? 1, 3, 5, 6, 7. 1, 3, 5, 6, 7. Finds that it's 4. 2, 3, 4, 5, 6, 7. So 7 and 7 is 14. 14 divided by 2. But it's going to be 4 and 4. It'd be 1, 1, 2, 2, 3, 3, 4, 4. So 4 divided by 2 is 4. Okay. Very nice. Okay. Let's go through and remove our print statements. Let's run it. Okay. That looks pretty good. Let's go ahead and submit and see what we get. So there we go. We have a runtime of... Oh, sorry. Hit the wrong button there. We have a runtime of 1 second. That beats most of them. Okay. Wonder where we could speed that up. Our memory efficiency is pretty good. Okay. Almost into the 2.3 because we're 2.28. But we're pretty good. Okay. I'm fine with the memory thing. Why is our runtime not in the fastest? Is there anything that I could do to speed up the runtime? I don't think there is. I'm not entirely sure if there is. I mean, it's a loop with an if check in it. A couple if checks. And then you could put this as an else and get rid of these two if checks. Or this if check. But I don't know. I don't think so. Yeah, sometimes you get it too where you submit your code, and if the servers are just being beaten up, and then it's a little bit slower. Let's just hit submit one more time to check. See if I can get the 1 extra millisecond off. No, see, now I'm 3 milliseconds. I didn't even change the code. So that tells me that the server's just getting hit. Okay, so I'm probably in the lower test case solutions. We're going to call that good. I mean, I solved it. It works. Our runtime is using a binary search through the two arrays, so we are in the order of log mn. We didn't use any extra memory because we're using references to their vectors, and we're not moving or copying anything around. All we're doing is some order 1 memory creations of U sizes and some value things here with the small min and max and big min and max and our mid values. So, yeah, I think that's a pretty efficient solution, and I think we met the requirements. Thanks for joining me, and I'll see you at the next one. End of line.